Until the 1920s, we thought our universe had just one galaxy, and that was the entire universe. And of course, we are at the center of it. I mean, why wouldn't we be? But then came along Henrietta Levitt, a young, underpaid astronomer working at the Harvard. She made a groundbreaking discovery that changed everything. Within just a few years, we realized not only is the universe teeming with billions of galaxies, but that the universe itself is expanding, and apparently made Einstein say that he had made the biggest blunder of his life. But wait a second, what exactly was that blunder? And wasn't it Edwin Hubble who discovered that the universe was expanding? What exactly did she do? And most importantly, why didn't I ever hear about her? Well, it turns out that we are always told an oversimplified story about how Edwin Hubble discovered that the universe is expanding. But when you look into the details, oh man, the details are a marvel of scientific thinking, full of paradigm shifts, all centered around her groundbreaking discovery. And so I thought I should make this video to set the record straight. So if you're ready to rediscover the real story of how we figured out the universe is expanding, let's begin. So let's back up a little bit, because it all starts when we ask a fundamental question to the man who started it all, Newton. So Newton, according to you, everything attracts everything else in the universe. If that is the case, and if the universe has been there forever, that was the dominant view back then, that the universe was eternal, then the question was, why hasn't everything just clumped together? And Newton's answer to this is, I don't know. He really had no answer for this question. So we move on and we talk to Einstein, who has a much better theory of gravity. Einstein, same question. And Einstein says, I do have an answer for you. What if at large distances, gravity is also having some kind of a repulsive force that could counteract the attractive forces and the universe could stay balanced? In fact, you can even see this in his field equations. See, the original field equation had the space-time curvature on the left side, a constant, and matter and energy on the right side. So matter and energy tells space-time how to curve. That produces the attractive gravity. But then he added in another term. The negative sign represents that it has the opposite effect on the space-time curvature of matter and energy. So this produces the anti-gravity repulsive force. And it does not depend on matter and energy. It is purely a function of space. And he tweaked this constant just to get the universe balanced. And he called it the infamous cosmological constant. So look, the universe was balanced. And at this point, I'm like, Einstein, did you just pull out this term out of thin air just to make the universe stable? And Einstein's like, yeah, but do you have anything better? Yes, I do, said Alexander Friedmann, a Russian physicist. Friedmann says he solved the Einstein's field equation for the entire universe by making some assumptions and realized you don't really need the repulsive term. In fact, he figured out, according to Einstein's equations, the universe itself can be dynamic. It can be contracting or it can be expanding. So look, he says, Einstein, the universe doesn't even have to be static, so we don't need this term at all. And Einstein's response to this was, wow, that makes no sense. And this is probably how the conversation went. Friedmann, give me your notes. Let me check. Hey, there is a mathematical error. And Friedmann says, no, there isn't. And Einstein's like, yeah, no, there isn't. But still, it doesn't make sense. What are you talking about? Space stretching and expanding? That doesn't make sense. Space has to be static. Everything needs to be balanced and the cosmological constant stays. That was a dominant view back then. And Friedmann's idea was just that. A wild idea. To make any kind of progress, we needed to start making some concrete observations. And that's exactly where our first unsung hero comes in, Vesto Slipher. Slipher was an American astronomer and he was tasked with, I kid you not, finding Martians. Why Slipher? Because he was really good at spectral analysis, where you look at the light, decompose it, and figure out what elements are present. So the hope was he could point telescopes at Mars and find evidence for life-giving stuff like water or breathable air, etc. Okay. So Slipher, what happened? Slipher says he was doing that, but in spare time, he was really interested in figuring out what these spiral-looking things in the sky was. And I'm like, Slipher, what are you talking about? These are Oh yeah, back then we didn't know that there were other galaxies. We thought that there was only one galaxy. I find it a little weird that there was a time not too long ago. I mean, relativity was discovered already, but we believed that there was only one galaxy. But if you think about it, we live in a similar time today where we believe there's only one universe. But anyways, coming back to this, Slipher was super interested in what these spiral-looking things were. They called them the spiral nebulae back then. So Slipher, what did you do? Slipher says, I did what I do best, spectral analysis. So I looked at the spectrum and he found something really, really interesting. He found that the light from all these spiral-looking things were mostly red-shifted. What does that mean? Well, you probably already know this, but remember, whenever a source of light is moving, then the light in the direction of the motion gets squeezed, making smaller wavelengths, and the light in the direction opposite to it gets stretched out, giving you longer wavelengths. And shorter wavelengths look to us bluish, and so we call that the blue shift, and the longer wavelengths look to us as reddish, towards the red end of the spectrum. We call that the red shift. If something is red shifted, we know it's going away from us, and if something is blue shifted, we know it's coming towards us. Okay, he found there were some galaxies like Andromeda, for example, were blue shifted, but most other galaxies that he noticed, about 30 to 40, were all red shifted. And so this meant that a few galaxies, which again, remember back then we didn't know, right? So we thought there were spiral nebulae within the Milky Way. But anyways, this meant that some of these spiral things were hurling towards us, and he could estimate the speeds. Speed was close to about 200, 300 kilometers per second. And the rest of the others were just moving away at staggering speeds. In fact, he found some of them were moving at about 2,000 kilometers per second, purely from the redshift. In fact, apparently he got a standing ovation when he represented this, because this was the fastest thing ever recorded back then. So the big question was, what did this mean? Well, for some people, this didn't mean anything. This was just an unusual phenomena. Maybe something is happening. Maybe the redshifts mean something else. I don't know, but this did not have any broader significance. But for some other people, including Slipher, this was maybe beginning to tell us that these things are not part of the Milky Way at all. And maybe they're questioning, just maybe, they're separate galaxies altogether. But remember, thinking of other galaxies was crazy talk back then. It's kind of like today thinking about other universes. You better have solid evidence if you want to talk about that in science. And this just wouldn't do. We needed something more. But I'm like, wait a second, why couldn't we just measure distances to these spiral-looking things? I mean, if we knew how far they are, we would know. But we didn't have the tools to measure distances back then, right? I mean, the best tool to measure distances back then was by using parallax. You know parallax, where the usual demonstration is you close one of your eyes, align two fingers, and then switch the eyes and you see the finger shifting. And what you notice is the finger that's closer to you shifts more compared to the one that's farther away. So that means whichever shifts more is closer, and if the shift is lesser, it's farther away. And we did the same thing with the stars. We call this stellar parallax. We measure from two different vantage points and we figure out how much the shift is. And in other words, measure this angle. By knowing this angle, we could estimate how far the star or anything else was. But the problem is, the farther the star is, the smaller this angle becomes. And after a point, this angle becomes just too small to measure anything. And therefore, the parallax had a range, and the range was roughly back then about 100 light years. Now, if you think about it, 100 light years, we could measure distances that took light 100 years. That is pretty incredible. But in the grand scheme of things, we believe that the Milky Way was about 30,000 light years. It's an underestimate. Today we know it's about 100,000 light years. But because the Milky Way is so big, even with parallax of range of 100 light years, it is nothing. And so everything was pretty much out of range. So if you tried to measure distances to these spiral-looking things, you wouldn't get anything. So you don't know whether it's at 200 light years or 2 million light years. There was just no way of knowing things. We needed some serious upgrades on our cosmic measurement systems. Kind of like the upgrade that I got on my internet security using NordVPN, who's sponsoring this video. Now, I know what you're thinking. Before you skip ahead, let me just tell you a quick short story. I get a lot of sponsorship requests, right? But most of them are actually spam, for example, which asks me to download a malware. Now, I think I'm pretty good at detecting all of those things, but recently one of my friends got his YouTube channel hacked. Now, it's fine, he's back and everything, but that got me a little paranoid, because it's when it happens to you or someone close to you, that's when it becomes real, and that's where the regrets sets in, right? Especially when we have solutions. And that's why I'm partnering with NordVPN. I mean, right off the bat, with just one click, I'm connected to a virtual private network. Now my IP, identity, and location are all hidden. I mean, if you try to check it, it shows I'm in California. I'm not going to tell you where I am. And for me, the real deal is actually this. It analyzes my downloads to check for malware and blocks malicious websites. And what's more awesome is that with just one account, we can connect up to 10 devices. So both my wife and I can now easily access public Wi-Fi without worrying too much. And it also doesn't reduce the download speeds or anything. Now, this does not mean I'll stop being vigilant. You should always be vigilant when you're online, but it just feels like attackers are getting more and more creative. And if I do slip up, I feel like Nord's got my back. So if you want to try it out, you can use my link to get the best deal. Just go to nordvpn.com/FloatHeadPhysics. There are some massive discounts on 2-year plans. Plus, you're going to get 4 additional bonus months. And by the way, another good thing is that if you try it out and if you don't like it, 30 days money back guaranteed. So that's great, right? So do try it out. You'll also be supporting me. That's nordvpn.com/FloatHeadPhysics. The link is also in the description. Now, back to the video. So we needed some serious upgrades in our distant measurement systems, right? And that's exactly where Henrietta Levitt comes in. She was hired as a human computer at the Harvard Observatory. What does that mean? Well, back then we didn't have a lot of computing power. So we had to manually analyze the data. And women were hired for that, mostly because you could pay them less. That's just how it worked back then. And when Levitt was meticulously analyzing thousands of data of thousands of stars, she came across a startling discovery that upgraded our measurement systems. So Levitt, what exactly did you do? So Levitt says, Mahesh, if you have a light bulb and you know exactly how bright it is, and then let's say you see a similar bright bulb but much dimmer, then that means that that bulb must be farther away. That's why it's appearing dim to you, right? So this means that if you know the apparent brightness of the bulb, you can compare it with the true brightness and you can estimate how far it is because of the inverse square law, right? And this also works the other way around. If you know how far it is and if you know the apparent brightness, well, you can find out the true brightness. You got that? This is going to be important. And I'm like, yeah, that makes sense. You're using brightness as a proxy to measure distances. So what you're saying, Levitt, is that we can use the bulbs in the sky, the stars that we have in the sky, their brightness as proxy for measuring distances. But wait, this would only work provided we had some kind of a standard star whose true brightness we knew and we could identify that we're looking at those particular kinds of stars. But stars shine with all kinds of brightness, right? So how does it work out? Well, Levitt says normal stars cannot be used for this, but there are certain particular kind of stars called Cepheid variables. And I'm like, Cepheid what? So variable stars are the ones whose brightness changes over time. It pulsates. And I'm like, that's just twinkling of stars, isn't it? And she says, no, Mahesh, twinkling of stars happens because of the atmospheric refraction. Here, the stars are truly changing their brightness, and this happens over days, not few seconds. And of those variable stars, Cepheid variables are the ones whose brightness changes in a very particular way. It has a signature pattern, which means by analyzing how the star's brightness changes, you can identify a Cepheid variable. And I'm like, that is awesome. Now I have some kind of a standard star, the Cepheid variable. But wait a second, this would only work if all Cepheids had the same brightness. Is that the case? And Levitt says, no, it's not. But, and this is where the story gets really interesting. Most of the times it gets oversimplified because there's some subtle science involved. But for you and I, this is the perfect moment. This is the climax because this is where the groundbreaking discovery happens. Are you ready? Okay. While analyzing data, she found about 25 Cepheid variables all in one spot, the small Magellanic Cloud. What's interesting is that she found that some had a much higher peak brightness compared to the other. And since they are in the same spot, which means they're pretty much at the same distance from the Earth, this variation is not due to the distance. This variation is truly because some Cepheids are brighter than the other, and she could now study them to see if there's any pattern. And she did find a pattern. She found that if you plot a graph of period of the Cepheid variables, the pulsation period on the x-axis, actually the log of the pulsation periods, okay? And the apparent peak brightness, it's apparent because it's the brightness that appears to you when looking from the Earth. If you plot this graph, this is what she found. That is a straight line. what she had figured out is a relationship between the period and the peak brightness. The shorter ones, the ones that have shorter periods, which means they fluctuate much more quickly, they have a lower peak brightness, and the ones that have much longer periods, they have a much higher peak brightness. And I'm like, this is all we needed, right? Now, if I know the period of a Cepheid variable, I know exactly how bright it is, right? And Levitt says, no, Mahesh, almost, because this is the apparent brightness. This is not the true brightness, but that's okay. Now, all we have to do is find a Cepheid variable within our parallax range. Then we know exactly how far it is, and then we can find its true brightness. And once we find its true brightness, we can use the Levitt's relationship, the period luminosity relationship, to find the true brightness of any other Cepheid. Long story short, because of Levitt's law, as we call it today, we understood what was the true brightness of any Cepheid. You give me the period, and you will now figure out the true brightness of that Cepheid. And you can use that as a standard for measuring distances. Isn't that incredible? So the big question is, how much of an upgrade was this? Well, remember, back then, the range of the parallax measurements was up to a few hundred light years. With Cepheid variables, that range increased to about 1,000,000 light years. That's right. This gave us a serious upgrade on our distance measuring systems, and now we had everything needed for discovering paradigm shifts in astronomy. So let's calm down. What happens next? Well, first of all, her boss named Harlow Shapley, who was the director of the Hubble Observatory, obviously got access to her publication, Levitt's Law. And he immediately started identifying Cepheid variables within the Milky Way, and he found that the Milky Way was actually much bigger than previously expected, roughly about 100,000 light years. But more importantly, he also found some Cepheid variables in the center of the Milky Way, and by calculating how far that was, he realized that it was about 30,000 light years away, which meant, again, we realized that we are not at the center of the Milky Way. And now we finally get to Edwin Hubble, a lawyer turned astronomer. He found a Cepheid variable in the Andromeda, which means he could now find the distance to it. And what did he find? Well, he found for the very first time the distance to the Andromeda to be close to 1,000,000 light years. This means for the very first time we realized that the Andromeda is not within the Milky Way, but it's much outside. And by looking at its apparent size, we now figured out that it must be much bigger, like a galaxy. This is how humanity discovered a new galaxy. This was huge. Remember, this is as huge as today discovering new universe altogether. Now, of course, we know that this was an underestimate. The actual value is close to about 2.5 million light years. But who cares? What matters is that pretty soon we realize that our universe is teeming with billions of galaxies. This now brings us to the most important discovery Hubble ever made. Remember how Slipher had already calculated the redshift values and had figured out how fast these things were already moving? But we didn't know what that meant. Now Hubble said, hey, let me just go ahead and find some Cepheid variables. Then I can figure out how far these things are. And he did that. In a few years, he figured out that all of these galaxies are millions of light years away. But most importantly, he found a beautiful relationship between the distance and the recession velocity. He found that the galaxies that are closer are moving away slower, and the ones that are much farther are moving away much faster. In fact, there was a beautiful relationship. When he plotted distance versus recession velocity, he found that they all lie pretty much on a straight line. This is called the Hubble's law. But what does that mean? Well, one interpretation was the most straightforward one, that the galaxies are indeed just moving through space. But there are two problems with that. Well, first of all, this means that our Milky Way comes at the center of all of this motion, and humanity has finally learned its lesson. We know that we are not at the center of anything. So this must be true from all perspectives, that everything must be moving away from everything else, as seen from any perspective. But more importantly, it doesn't also explain why things that are farther away are moving faster. So what model can fit this observation? Friedmann's model. Remember how Friedmann had suggested theoretically, just by solving Einstein's field equation, that the universe itself could be stretching or contracting? But now let's see what happens if the universe itself stretches and expands. Well, see properly, what we find, look, the ones that are closer move away at a shorter velocity, and the ones that are farther, they move away a lot more, exactly aligning with Hubble's law. And notice there's nothing special about Milky Way. If I change the vantage point, let's say I look at the same thing, this expansion from this perspective, I get the same result. Now, boom, you see that everything is moving away from this one according to the Hubble's law. That is beautiful, isn't it? This is how we realize that the universe must be expanding. The Friedmann's model perfectly fits the observations. And pretty soon we realize that if the universe is expanding, then if you wind back the clock, it must have had the beginning. And so the Big Bang hypothesis was put forward. Actually, not really. There is a strong counter-argument put against the Big Bang. There's a way to imagine the universe expanding without ever having a beginning. And that's homework for you. Look up something called the steady state universe. And you can also see how we eventually disprove that. Because at the end of the day, it's about scientific thinking. So don't just take my word for it. Do some analysis yourself. But anyways, the point of the story was that we made some groundbreaking discoveries, like Shapley discovering that the sun is no longer at the center of the Milky Way, or Hubble figuring out that the universe is expanding. But they couldn't have done it without Leavitt's law, without her meticulous analysis and discovery of the Leavitt's law. This wouldn't have been possible. And they were openly crediting her for their work. In fact, Hubble even mentioned that she deserved a Nobel Prize. And so when someone actually tried to nominate her for a Nobel Prize, unfortunately, she had suddenly passed away because of a stomach cancer. Anyways, Einstein finally realized that Friedmann was right. We did not need to force fit this particular term because the universe is not static in the first place. So he got rid of the cosmological constant, stopped working on it, and apparently called it the biggest blunder he had made in his life. Or was it?